can start on time. Here. Alrighty. Trusty thing. Watch it always my fault just to make sure there's some time. Oh, something is my. Can you hear me okay?
Your video seems to be frozen, but I can hear you and the screen.
Okay, well, I'll start now and then I'll try to take care of the video later. It's the video and so let me make this video again. Yeah, so welcome everybody to the online SPICE-SPIN+X seminar series that I lead here together with the help of Alexander Mook, which now in Münster is actually the speaker, Libers Mekiel in Dresden, MBA Dresden, and Wittmann here in Mainz, Guy University in Duisburg, and in collaboration with the Research Center of Collaborative Research Center of SPIN+X, led by Martina Schliemann and Hillebrands in Burkhard Hillebrands in Kaiserslautern, and Matthias Klaue here in Mainz. As usual, this is a webinar format, so please write your questions in the chat or in the Q&A, and I will pass that along to the speaker later on or during the talk if it's necessary. And then please check out as we go along the schedule for the next talks. So today's a pleasure to, of course, welcome Alex, who was in Mainz and moved recently to Münster to start his own group. He did his PhD in Halle under the guidance of Ingrid Merteg, and went on to do a postdoc position in Basel, and then here in Mainz, is really in his own Emergent group, and now in Münster. He's worked on several aspects of magnetism, but particularly quantum magnetic systems, quantum geometry, and topological systems, particularly of the magnetic sector. And there are several awards. One of them was the recent one here in Mainz, the Sibley Kalkov Rose University Prize, and also, of course, as I mentioned already, the Emergent as well. So with this, I'm going to stop sharing and ask you to go ahead and begin your talk. And bring back some people.
Thanks, Jairo. Let me just go to the right sharing. All right. So thanks again, Jairo, for the kind introduction and for the invitation to give a talk in the SPICE-SPIN+X seminar. It's great to be back. Now, in this talk, I would like to tell you a story about how we can functionalize antiferromagnets, in particular in the direction to make them show altermagnetic properties. The main idea here is that we look at the largest class of magnetic materials, which are the antiferromagnets, and we wonder if we can make them useful in the sense of altermagnetism. And in particular, we will be looking at surfaces of antiferromagnets and show that one can cut antiferromagnets in particular ways to make their surfaces altermagnetic. Now, this line of research has the global motivation that there is ever-growing energy consumption of our technology. Already 6 years ago, data centers of this world were consuming more energy than some countries. And with the recent advent of GPU computing and AI, this increase is just speeding up. So one pathway towards new technology is, of course, given by the field of spintronics, which is concerned with the spin degree of freedom of electrons, and there in particular magnets are important. And for the rest of this talk, we will be concerned with collinear magnets. And we have learned from Libor, Jairo, and Tomasz that the collinear magnets can be classified in three different categories. There are the ferromagnets, which are uncompensated in real space. And this net moment then leads to a Zeeman splitting of the electronic band structure, which is isotropic. Isotropic meaning that if I sit at the gamma point, I see a splitting, and no matter in which direction in K-space I'm looking, the sign of the splitting is the same, such that the leading partial wave decomposition of the splitting is an S wave. Now, the second class of collinear magnets are the antiferromagnets. Here the order is compensated in real space, and there is a spectral symmetry which relates the two sublattices. It's either a translation with time reversal or also inversion symmetry supplemented with time reversal. And these symmetries lead to a Kramers degeneracy of the electronic band structure, such that essentially you have no splitting at all. But then there is the third kind of collinear magnetism, which goes under the name of altermagnets. They share with antiferromagnets that the spin order is compensated in real space. However, there's no translation symmetry between the two sublattices and also no inversion plus time reversal. But instead, it's a symmetry which flips the spins and would require, for example, a rotation in spin space. This symmetry then does not lead to a Kramers degeneracy, which is why you can have spin splitting of the electronic band structure. However, it cannot be S-wave because that would require ferromagnetism. And instead, the leading partial wave decomposition of the splitting would then be another even parity splitting, which depending on the symmetries of the system could be a D-wave, G-wave, or an I-wave. Now, from the perspective of spintronics, of course, we are used to deal with ferromagnets. They are exciting from the point of view that they are technologically extremely useful because their magnetization can be easily manipulated and they are spin active. For example, we can run a charge current through the system if it's a metal, and then we would obtain a spin polarized current simply because there are more spin ups than spin down, for example. However, we would have the problem that ferromagnets are only working at gigahertz speeds, and they have stray fields, which is a bottleneck for the scalability. Now, in contrast, antiferromagnets have two very positive properties. They have a terahertz dynamics and no stray fields. Alas, since there's a Kramers degeneracy of the electronic bands at the level of non-relativistic physics, they are spin inactive. So one would need spin-orbit coupling, which is a weak energy scale, to make them useful. And this is where altermagnetism really shines. It combines the best of the two worlds, meaning it shares with antiferromagnets that we have the terahertz dynamics and the absence of stray fields, but they are also spin active. For example, in a D-wave magnet, as indicated here, I could apply an electric field in X direction and would get a spin polarized current. If I rotate the electric field by 90 degrees, I would again get a spin polarized current, but with the opposite spin polarization. If I applied along the 45-degree direction along a nodal line of this partial wave, the D wave, then one would not obtain a longitudinal current, but a spin splitter current. All right, let me quickly remind you where this classification comes from. So we are used mainly to deal with magnetic groups, and in magnetic groups, we couple two parts of the Hamiltonian that describe our system. So we couple two energy scales. We have on the one hand the exchange physics, so the magnetic Hamiltonian, and then a smaller relativistic correction which comes from the spin-orbit coupling. And magnetic groups say, okay, since they are both coupled, then all the symmetries that I would apply to the crystal, I should also apply to the magnetic system. The main motivation is something like this. If you have a magnetic ion which has an octahedral environment and you elongate it, you distort it a bit, then you might get a local crystalline anisotropy axis. So when you rotate the crystal, you rotate the long axis of the octahedron, the distorted octahedron that is, then you also rotate the spins because they would follow this easy axis. Now, magnetic groups are extremely useful, but the problem is since they couple magnetic magnetics with the relativistics, you would get the same magnetic point group here, M prime, M prime, M, for vastly different magnets. So here, for example, this is a coplanar but non-collinear antiferromagnet, which has the same magnetic point group as a ferromagnet or a collinear compensated system. In contrast, if you want to describe only the symmetries of the magnetic systems and you neglect the relativistic corrections, then you would be able to use spin symmetries which could tell apart the coplanar from the collinear order. So let me show you how this then looks like. So for example, consider an electronic band structure like the one shown here, which has a strong exchange-driven splitting. So you would look at this and you would say, well, okay, this clearly has a C4 symmetry, which I maybe have to supplement also with time reversal to flip the red to the blue color. But in magnetic symmetries, I would have to apply this C4 plus time reversal symmetry both in the spin sector, which is shown here to the left of the double bar, as well as to the real system, which is shown to the right. So if we first act with C4 both in spin and real space, then with time reversal symmetry, we would end up with a system which is not the system that we started with, which is shown here again. In contrast, in spin symmetries, we can apply a different symmetry in the spin sector than in the magnetic sector. So we could rotate by 90 degrees in real space and then by 180 degrees in spin space. And this then is a good symmetry of the system and describes the exchange physics. Now, okay, this is symmetry, but we can also gain some physical intuition why this would lead then to this D-wave splitting, for example, for the altermagnets. Let me show you a simple example because this motif will be reappearing throughout the talk. So let's assume we sit on a square lattice with an compensated magnetic order. So the cyan and the magenta show spin up and spin down. And let's build a simple hopping model with only one orbital per side, then T1 is our nearest neighbor hopping. And let's decorate this lattice with a non-magnetic atom, which we only put in a checkerboard-like pattern, let's say on the black squares of the chessboard. We could integrate this out and build an effective model with second nearest neighbor hopping along the diagonals, for which we would have to use different parameters because hopping via a non-magnetic ion is different than hopping through a plaquette without an atom. Now we can convince ourselves that this is not an antiferromagnet anymore because it doesn't have any of the properties which make the system antiferromagnetic. Concretely, there's no translation plus time reversal symmetry because we would translate a dashed side onto solid, a dashed bond onto solid bond. And there's also no inversion symmetry connecting the two oppositely polarized sublattices because we would have the same problem with the dashed and solid lines. However, what we have is a spin symmetry, this C2, C4 symmetry, and we can directly see that this would lead to a D-wave spin splitting. Let's consider the situation that the dashed hoppings are 0. And let's also set the T1 hoppings to 0. In that case, we end up with decoupled chains with a ferromagnetic order. That means the electrons which live on the horizontal chains, they see, let's say, a positive Zeeman field or Weiss field. So they would have positive splitting and they would only acquire dispersion or velocity along the x direction. In contrast, along the y direction, they would be completely flat because the chains are decoupled. In contrast, for the 90-degree rotated chains with opposite Weiss field, we would get opposite splitting and the dispersion along y direction and a flat band structure along the x direction. So you can directly see, okay, this structure would lead to a D-wave pattern where there is a nodal line along the 45-degree direction. Now, the motivation for what I'm going to show you comes from different directions. One motivation comes from the 2D altermagnetism, so altermagnetism in monolayers. I show you here two early examples. For example, such a checkerboard pattern is realized in a monolayer of iron selenide, where you see the magnetic ions here. If you then apply an electric field to the system, you would shift the selenium atoms a bit up so that one square is different from the other. And then you would see again this D-wave splitting in the electronic band structure. So 2D magnetism is of course interesting also for applications. And from this point of view, there is also interesting recent experiments. Something seems to be going on at the surfaces of altermagnets or antiferromagnets. Surfaces are of course particularly interesting for device applications. So let me walk you through this experimental data. We are looking here at a system which is built from a stack of layers, and this layer is vanadium oxyselenide, which essentially shows again this checkerboard type model which I've shown to you in a second ago. Now in this paper, the author synthesized a potassium intercalated version of this, which means you have these altermagnetic monolayers, which are then separated by potassium. The authors conducted a spin and angle resolved photoemission spectroscopy. And in this data, they were able to see D-wave altermagnetic splitting. So concretely, what they show us here an integrated result of the spin polarized signal, and for two different cuts in the Brillouin zone. So for example, in cut 1, one would expect from DFT calculations, assuming such an altermagnetic stacking, that one would first cut through a blue band, then another blue one, then a red, and then another red, with the color indicating the spin. And indeed, this is what the experiment shows. For a different cut, one would first cut through blue, then a red, then a blue, then a red band. This is what one sees in experiment. So indeed, there is photoemission spectroscopy data, which is compatible with altermagnetism. And it was interpreted that this system is built from altermagnetic monolayers, which are stacked in a ferromagnetic way so that the bulk is a D-wave altermagnet. There is similar results showing altermagnetism for the rubidium and the cesium intercalated compounds. Alas, for this potassium intercalated system, neutron diffraction, which measures the bulk, says that the system should be an antiferromagnet. So the question is, how can we reconcile this experimental data with the neutron diffraction data? And we remember that photoemission, of course, is a surface-sensitive technique. So the question should be, what happens at the surface of such a system? Now, this is the question we set out to answer together with this team. So this is a collaborative effort of Libor Schmekal at the Max Planck Institute for the Physics of Complex Systems in Dresden and Jairo Sinova's team at the Johannes Gutenberg University in Mainz. And I'm going to show you the contribution of everyone in this team. The main question is really, how does the altermagnetic symmetries emerge at the surfaces of collinear antiferromagnets? Because if we understand this, we would be able to take the entire large class of collinear antiferromagnets and functionalize them by identifying surfaces with altermagnetic properties. All right, let's first develop some intuition, which is inspired by this compound that I just introduced to you. So let's do the following. Let's take our checkerboard model, red and blue, again indicating the magnetism, and let's stack it in a way that the checkerboard type pattern is staggered. So this introduces a PT symmetry in the bulk, and PT symmetry tells us that the system should be a bulk antiferromagnet. And indeed, using some representative parameters of this toy model, we see that we have a spin degenerate band structure, meaning each electronic band is twofold degenerate. Now note that we couple these layers inspired by the one-dimensional SSH model. So we have a U and a V coupling that is different. So let's assume we terminate the system at the 001 surface. Then let's go to the limit where V is 0. In that case, we would have a single dangling layer. And for a single layer, we already know that there's altermagnetism in the system. So we do expect, when we look at the spectral function spin resolved at the surface, we would expect altermagnetism. So now if we turn on small v, which couples the dangling layer to the rest of the layers, we do indeed see, as a function of energy and along a high symmetry path of the surface Brillouin zone, that the surface spectrum clearly shows a spin splitting. And the D-wave pattern becomes particularly obvious when we look at an isoenergy cut in the surface Brillouin zone, where we can nicely identify the D-wave splitting of the bands. All right, so this is an academic example, right? So we have built a model where we knew what to expect, and altermagnetism emerged kind of by instruction. Now the question is, if we were given any collinear antiferromagnet, how would we be able to tell which of its surfaces would be altermagnetic? And here I remind you that we know the three-dimensional spin groups from the work of Libor, Jairo, and Tomasz, and there we know that the point group elements which cause a degeneracy throughout the Brillouin zone are those elements where we have a C2 in spin space and either the identity or parity in the real space sector. We also know that in 2D, the situation is slightly different. So if we look at the 2D spin point groups, also called the 2D spin layer groups, then it's not just identity and inversion, which would lead to the spin degeneracy, but there are two more symmetries. In particular, there's a C2 symmetry around the normal of the layer, because this inverts the x and the y directions, and it acts as if you are inverting the full two-dimensional reciprocal space. Similar argument can be brought forward for a mirror symmetry. Now, when dealing with a surface, we kind of live in between, because for a semi-infinite system, we have a three-dimensional bulk which gets terminated at a two-dimensional surface. And we can already expect, well, okay, there's the identity, and the C2 around the normal of the surface would also be part of the symmetry, which part of the group which could lead to a spin degeneracy. But by construction, the surface breaks the inversion symmetry, and it also breaks the mirror, because the surface can never be a mirror for the system, because one half space is vacuum and the other one is material. So we have to look at this separately. And we try to answer this question now by going along a very technical way, but very constructive. We say, well, okay, we are given some material, and for that we can determine the bulk spin space group of this material. And we ask the question, what happens if we cut it along a particular surface n? So what we want to determine is the surface spin space group. Surface is always indicated with a n. So now we look at all the elements which are part of the bulk spin space group. Just as a reminder, we have the spin symmetry, and then in real space we have a point group element, and since we are dealing with a space group here, we also have a translational part. And then we follow a construction similar to the surface magnetic groups, where we say, well, okay, to qualify as an element of the surface spin space group, we better don't change the surface. So this means that we say the point group part of real space should not change the surface. So the surface should stay the surface. So the normal cannot change. And also we only allow for elements which have a translation within the surface, simply because we cannot translate in normal direction, because simply there is no material. So now in principle that we have the surface spin space group, we can project out the translational part and produce the corresponding surface spin point group. And then to analyze altermagnetism, the technical step here, we have to bring back the effective inversion symmetry from the spin-only group, which describes the operations in spin space only, which then constructs a surface spin Laue group. And these are the objects which we can discuss and analyze for their altermagnetic properties. Okay, let's go back to the example to see how this looks like in action. So first of all, we can verify that the bulk of the material is actually an antiferromagnet. And we do so by finding that the bulk spin point group is given by this expression. So the crystallographic Laue group is 4 over MMM. And we see that all of these elements either appear with identity in spin space or with a C2 in spin space. And this is the defining property of an antiferromagnet. Now at the 001 surface, we break down the symmetries, in particular the surface spin point group would only include a 4-fold rotational axis where we have to flip the spin, indicated by this little 2. And then there are 2 more mirrors, which are orthogonal to the rotation axis. And one of the mirrors comes without spin flip, and the other one comes with a spin flip. So overall, the corresponding spin Laue group, where we bring back the inversion symmetry of the spin-only group, looks like this, where we see that there's the halving group MMM, and only the elements of MMM come with the identity in spin space, while the set difference between 4 over MMM and MMM comes with the spin flip. In particular, an element which is part of this set difference would be this element where we have the C2 in spin space and the full rotation symmetry in real space, which gives rise to the D-wave surface spin splitting in the electronic band structure, which we had calculated explicitly before. All right, so this shows one example, an example of D-wave character where the surface spin point group and the corresponding surface spin Laue groups were shown to yield spin splitting at the surface. Now we can go and classify all of that. And in particular, we find 7 groups, 7 surface spin Laue groups that show altermagnetism with the usual categorization into D-wave, G-wave, and I-wave. And these 7 groups correspond to the 2-dimensional spin layout groups. In total, though, there are 11 groups. There are 4 more groups which are not antiferromagnetic in the sense that the point groups don't include the time reversal symmetry. But these 4 groups don't allow for a non-relativistic spin splitting at the surface. I'm going to explain this in the second part of my talk, but let's first ask the question, which materials have surfaces of this type? So Colin and Rodrigo set out and looked at the Megan-Data database, where we find experimentally reported magnetic structures. So there are in total 2,700 magnetic structures reported in this database, and 755 can be identified as collinear antiferromagnets, which means in particular that these are candidates to look for interesting surface normals for our algorithm. So in total, we looked at the 755 material entries in the Megan-Data database and then looped over all sensible surfaces. And we found that 1/3 of these materials have at least one altermagnetic surface. By that we mean at least one surface which belongs to one of the 11 surface spin Laue groups that I introduced a second ago. In contrast, a bit less than 2/3 has no altermagnetic surfaces whatsoever. So we concentrate now on this red part of this diagram. The detailed analysis then shows that we have a large portion of these surfaces which have a non-relativistic spin splitting, and an equally large share of materials come with this spin-degenerate surface altermagnetism, which I'm going to explain later. So essentially, what you would find in our archive paper is now a long list, which we have sorted alphabetically from A to Z. And for each of the materials that have at least one altermagnetic surface, we show all compensated surfaces and indicate whether the surface is antiferromagnetic, whether it has this spin-degenerate surface altermagnetism, or if it has this altermagnetism that really allows for spin splitting of D, G, or I wave character. Now let me show you some examples. So for example, we can look at sodium, manganese, phosphorus, for which we see that there are different surfaces all of which have D-wave character, but different surface spin Lowell groups. So together with Atachi and Xante, we then perform DFT calculations for this material, which is shown here. So we have layers of manganese, where we again see this checkerboard type pattern. And in between, we have the sodium atoms. The Néel temperature is very close to room temperature. And within the DFT calculations, we are able to reproduce the magnetic moment also found in the experiments. Now, so this structure is an antiferromagnet in bulk. In particular, it has a PT symmetry between the red and the blue atoms, which simply means that the bulk band structure is Kramers degenerate. And indeed, the explicit calculation shows this. So I show here in red and in blue, spin up and spin down, and we see that it's degenerate throughout the Brillouin zone. So the system is semiconductor, but we can now simply look at the surfaces of the material. So there are two surfaces of interest. One is the 0,0,1 surface, the green one, and the other one would be the 1-1,0 surface. Now let's concentrate first on the green surface, because this is the one for which we had already developed some intuition. In particular, one can show that this also has the C2-C4 symmetry. And what I show you here is now for the green surface, a spin-resolved spectral function at the surface. So we assume that we terminate the crystal at this surface, and I show you here along some carefully chosen direction of the surface Brillouin zone how the spectral function of the spin-up channel looks like. And now I show you the same for the spin-down channel, and we see if I toggle between the two that they look different, where we can already expect, okay, so there has to be a spin splitting at the surface, which becomes particularly obvious if I show you an iso energy cut at this energy, where indeed we see within the surface Brillouin zone, indicated by the dashed line, that the difference of spin up and spin down yields this nice D-wave pattern. So indeed, at the surface of this bulk antiferromagnet, we get a D-wave splitting of the electronic states. All right, so this is the green surface, which sort of realizes what we have already learned from the toy model. But the algorithm says that also the brown surface is altermagnetic. So for the brown surface, there's no C4 symmetry, which one can see immediately. There's not a 90-degree rotation, but it still has some mirrors, which make the system D-wave. So a similar analysis to the green surface shows then in the surface Brillouin zone that we have spin splitting. So we get contrast here, red and blue. And we see that there are mirrors which lead to a compensated, or to an overall compensation between up and down. In particular, I would like to emphasize that our algorithm now says that all of the compensated surfaces of sodium, manganese, phosphorus are altermagnetic, meaning that there's no way to cut this material to make the surface antiferromagnetic. There are, of course, for all material surfaces which would make the system a ferromagnet in the surface, because if you cut the system along any direction, there are no symmetries surviving at the surface. So it would be an uncompensated surface. But for this material, all the compensated surfaces are altermagnetic. This is not the general case. We can have a look at another material, iron germanium 2, for which we see that we get two different surfaces. There's the 0,0,1 surface, which predicts now G-wave altermagnetism. And there are two other surfaces where this system would be antiferromagnetic. Now let's have a look at this interesting surface for which we get the G-wave magnetism. Now, iron germanium, again, is an antiferromagnet in bulk, has a Néel temperature, again, very close to room temperature. And within the DFT calculations, we are able to reproduce the experimental magnetic moment to good quality. And we see that the germanium, which surrounds the iron, looks pretty complicated. In particular, there is a glide mirror symmetry, which eventually will be responsible for the G-wave symmetry at the surface. In bulk, however, we have a simple PT symmetry in the system, which renders the system an antiferromagnet. And indeed, the bulk calculation shows the spin degeneracy of the spectrum. Now, we look at the 001 surface, as indicated here. Again, along a direction where the spin splitting is finite, we see spin up and spin down channels. It's a function again of energy and has some direction in reciprocal space. And if you concentrate, for example, on this portion here, you see that this spectrum for spin up looks different than this part for spin down. So if I now show you the Fermi contour for this metal, one indeed sees the G-wave splitting. Particularly, you see that we have 1, 2, 3, 4 nodal lines, which is exactly what one would expect from a G-wave system. All right, so these are two examples for which we have DFT calculations. But let me point out some more materials on this list which could be of interest to you. So for example, our algorithm also predicts that manganese 3 platinum in its tetragonal phase, where it is a collinear antiferromagnet, has an altermagnetic symmetry. I emphasize that this is a different phase here from the manganese through platinum, which orders non-collinear. But there's also this tetragonal phase. Now, for this system, only the 001 direction is D-wave. Other surfaces, for example, 100 is an antiferromagnet. So let's quickly have a look at the surface, which is antiferromagnetic, just to make sure that we understand what's going on. So at this surface, you can see that there's a translation symmetry here within the surface, which when supplemented with time reversal symmetry is a good symmetry of the system, which is the defining property of an antiferromagnet. So it's only a special surface in the system which produces the altermagnetism. Now the situation is different for these magnetic plates, where again the 001 direction shows a D-wave system, but the diagonal cuts through the system, so the 110 surface, for example, is also D-wave, but with a different surface spin-Laue group. And now, in contrast to the system I just explained to you, the 100 directions are not antiferromagnetic, but have the spin-degenerate surface altermagnetism. If you're interested in DFT calculations on the 001 surface of this material, I refer you to this paper. Now, there are other materials which are interesting also from the field of antiferromagnetic spintronics. For example, the orthorhombic phase of copper manganese arsenic has one compensated surface, and this turns out to be a D-wave system. Now, this is really interesting because now, since we know that orthorhombic copper manganese arsenic is also a topological semi-metal, we would expect an interesting interplay between topologically enforced surface states and altermagnetic spin splitting. If you're interested in this direction and toy models that realize this, I refer you to this paper. Now I've shown you that we have D-wave systems and that we have G-wave systems. There's also one candidate on this list which can realize surface altermagnetism with an I-wave symmetry. It's a strontium ruthenate compound where the magnetic ions form a honeycomb layer, and the 001 surface of this compound is then predicted to be I-wave. Now, okay, I emphasized so far these 7 groups here where we have the clear non-relativistic splitting of the electrons. Let me quickly say something about this spin-degenerate surface altermagnetism. For that, let's have a look at another star of antiferromagnetic spintronics, which is manganese 2 gold, which is a PT antiferromagnet, but it has no TT symmetry, so no translation symmetry in the bulk. If we look now at the 100 surface, we can verify that this is not an antiferromagnetic surface. So the P in PT is broken obviously by the surface, and there's also no translation symmetry between these two magnetic layers, which when supplemented with time reversal symmetry would be a good symmetry, simply because the symmetry is already absent in the bulk. However, there is one of these symmetries, which I indicated in the beginning, are important for two-dimensional systems. Namely, we can rotate by 180 degrees around the surface normal and then flip the spin. And this symmetry produces the spin degeneracy in the surface Brillouin zone. However, it's not an antiferromagnet, meaning the point group doesn't include the time reversal symmetry. And microscopically, the difference is that although the system is compensated, we still have a ferroic order of the multiples of the spin density in real space. So there is this ferroic order of the multipoles. However, the surface happens to cut through a nodal plane of these multipoles, which is why there is no spin splitting on the non-relativistic level. Now, these groups have been encountered before also in two-dimensional systems. I refer you to this paper. And it has been pointed out that the difference to antiferromagnets should then really become explicit once you add backspin orbit coupling into the game, because then the time reversal symmetry becomes appreciable in all those effects which require spin orbit coupling together with time reversal symmetry breaking. It would be something like anomalous Hall effect or magneto-optical Kerr effect. So overall, for manganese to gold, we get different spin degenerate surface altermagnetic surfaces. And the same is true for the tetragonal phase of copper manganese arsenic, which also has this spin degenerate surface altermagnetism. There are also magnetic insulators that would have surfaces of this type. In particular, there's chromia, which is already studied a lot when it comes to surfaces. And we believe that, again, it could be very interesting to look at these particular surfaces from the point of view of altermagnetism with spin orbit coupling then. All right, so these are the materials I wanted to highlight from the list. Of course, we invite you to take a look at this list to see if there are materials that are close to your heart or that you might have lying around, and we are happy to discuss any other materials with you explicitly. I would like to add maybe two more afterthoughts to this list. One is that I just want to repeat what we did to make sure that I explain the difference to yet another possibility. So what we did is we looked at, let's call it symmetry-induced surface altermagnetism. So we start with symmetries of a three-dimensional antiferromagnet, which are the bulk symmetries. And then we ask about the symmetries or the symmetry breaking, to be precise, of a particular surface, which then leads to the surface altermagnetism. And here we have assumed that we have a pristine surface. So we literally cut through the system and say, okay, the crystallographic structure doesn't change. Of course, at any surface, one would expect relaxation effects. For example, the lattice constant along the normal direction would definitely relax. There can also be something more drastic, like a surface reconstruction, which really is also the unit cell at the surface as compared to the one in the bulk. And the magnetic texture, of course, could also change at the surface. So this is something that one would still need to analyze. However, given the great control that we have over surfaces and the knowledge that many surfaces don't relax too much, we believe that the surface altermagnetism can be easily detected in experiments. However, the idea of a surface reconstruction already gives a hint at what other mechanism could be at work to produce surface altermagnetism. In particularly, one could have a three-dimensional antiferromagnet and consider an antiferromagnetic surface. Then it could be that the surface reconstruction doubles the unit cell in a way which renders the surface an altermagnet. In that case, however, one would really have to consider the chemistry of the surface and would have to run detailed DFT calculations to make sure here symmetry alone would not be enough to tell that there is surface altermagnetism. So now we can actually come back to the experiments that I was advertising in the beginning, because we now have the theoretical framework to fully understand what's going on at the surfaces here. So we have the neutron diffraction data, which says that the bulk is antiferromagnetic. And we have the photo emission data, which is surface sensitive. which actually probes the D-wave surface in the system. So the two experiments are both right. It's just that the interpretation of the photo emission data would be already a proof of the surface altermagnetism. Now, further proof of surface altermagnetism, of course, could be produced with other surface-sensitive techniques, such as spin-polarized STM or surface transport. One could consider the situation that the bulk is an insulating antiferromagnet, but the surface is metallic. Then one could expect on the non-relativistic limit in the D-wave surface that there is the spin splitter effect. And of course, with spin-orbit coupling, one could also hope to see an anomalous Hall effect and also magneto-optical Kerr effect. All right, with this, I'm at the end of my talk. I think the main message is simply that we have a long list of materials now, which increase the total number of materials that could be studied for altermagnetic properties. We invite you to take a look at this list and see if you are interested in surface altermagnetism. You find everything in our archive preprint. And yeah, at the very end, I would like to thank the entire team again, which was working on this topic. And I thank the funding agencies for the money. And I thank you so much for your interest. And I'm looking forward to answer your questions.
Thank you very much for nice talk on our work. So let's see, people have questions, please raise your hands. Let's begin with Igor. Can you maybe unmute yourself and ask your question?
Yes. Okay. Thank you first of all, this beautiful talk. I was waiting for a long time for somebody to do this work. And I want just to voice a few comments in support of what you are doing.
Perfect. Please go ahead.
We like that.
Can you maybe put back the slide number 41, the previous one?
Yeah.
Right. First of all, it's not exactly true that the photo emission paper was correct. It was correct in terms of photo emission, but they also presented a patently incorrect neutron data, which you could see even before this other paper appeared, and claimed that it was ferromagnetic ordering between the layer, which would make it bulk altermagnet. And we were fighting with that for months before the experimental paper appeared, because we found that in DFT, we literally cannot beat it into ferromagnetic ordering between the plane for no matter what, with doping, changing constituents. There was one very odd exception, but basically the whole family has this property. Yeah. At least in the calculation.
Yeah, that's what our suggestion is. Yeah.
Yeah. So in that sense, this surface property becomes extremely important because the material itself is very useful. Second, again, you mentioned that, but I was sort of putting George Savatsky hat when he hears about surface. He always says that uncompensated surface cannot survive. So, for instance, in like sodium manganese phosphate, he would say that you would have sodium sticking on the surface no matter what, or you would have severe reconstruction, which you also said. I just want to emphasize that that just straight calculations should be taken with a grain of salt by material scientists, but most likely it won't change the general conclusion. And finally, I have one question: how you are proposing to use spin polarized STM to check for surface altermagnetism, quasi-particle scattering, or how? Because directly you cannot see it, right?
So I would hope that, for example, you could measure the spin polarized Friedel oscillations around the defect or something like this.
Okay, so this is
quasi-particle symmetry of the surface.
QPI. QPI. Yeah, that's tough, in fact, but we discussed it with some STM people. Anyway, all right.
Thank you so much, Igor.
Okay.
Actually, I think that you just answer the answer on related to the STM that is online. Let's see, Lucas, can you go ahead and please ask your question?
I just have a simple question regarding this ARPAS. You are, I think, a theorist, so you maybe don't know, but maybe someone in the audience knows. What about magnetic domains in this material? Because ARPAS will integrate them unless, well, one should check what they are before making claims, maybe.
Well, they definitely didn't, because the experiment showed, I mean, the experiment is very clear, altermagnetic in the ARPA signal. So that means that the domains that they have in there are large enough for them not to average out to zero. Otherwise, they wouldn't have observed in the experiments that were reported. The puzzle was that in the bulk, you had then you had afterwards with neutron scattering data correctly assigned, I guess, showing that it's antiferromagnetic in the bulk. And this was the puzzle about the two. So the fact that you have already in the ARPAS data that were reported on this material and the related one, that they are fairly large domains. You will always have domains, of course. There's no
I
question.
think even beyond the domains, one could add even to the confusion or to the things one would worry about at the surface, that you would also have terraces, right? And you can already imagine if you have a terrace with opposite, so if these layers are now oppositely stacked, like in an antiferromagnet, then different terraces would have opposite altermagnetic splitting. So for the surface altermagnetism, when you have an experimental probe that integrates over large areas, you would also want to have a single terrace ideally, not just domains. So
Yes,
Lucas, while this is not answering your question, it's just adding to the confusion.
I don't, maybe I understand that you cannot probably answer this question, but if then the proof would be to actually see the opposite spin splitting on the two opposite terraces.
Exactly.
Otherwise, different things can be measured, of course, in ARPAS, but if you would see two different, like really opposite spin on the two different areas,
with different orientations,
and scan around the sample, maybe make a picture of the sample showing, different domains and different areas. I think this is very important because, as you know, in spin polarized photo emission, you put any material and you will get spin polarization, and it will probably be, there will be some angular dependence of this spin polarization. This is all the people who do one-step model can calculate it. And it doesn't have to come from altermagnetism. It can come from, you put gold, you will also have spin polarization, right?
That's from the geometry of that's just from the geometry of the measurement, yeah.
Okay, thank you.
Great. There is, let's see, there's also a question from, I think, Alexandra, but she's not joining. Maybe I'll make her to see if she can. Alexandra, can you unmute yourself and ask your question, or should I read out your question? So let me see. Is it, so she writes in here, is it expected that the surface emergent altermagnetism can be maintained in heteroepitaxial interfaces or material interfaces in general, or with the chemistry the interfaces become important consideration in the emergence of this the ordering itself?
Right, that's a very good point. So in principle, one could extend the analysis that we did, where we just looked at the surface to vacuum, to the situation where you have an actual interface, because then the symmetries of the other material that you're interfacing the magnet with could further break down the symmetries. One could think about interface spin to do the same analysis. I mean, as long as the system's epitaxial, then I think this symmetry analysis would give very good guidance. But of course, again, the same with the reconstructions. I mean, one should really understand then also the chemistry of the interface, because if it reconstructs in weird ways, symmetries can be different than the symmetry analysis would tell you.
Okay, is there any, please, whoever has more questions, raise your hands. If not, I think there was a question of the STM, spin polarized STM already, about the surface that you already answered. I think Raphael, let me actually bring up Raphael. So go ahead, Raphael. Let me see if he's, can you ask your question, Raphael? Unmute yourself and ask your question.
No, it's working. Hi.
Hey, Raphael. Good
hi,
to see you.
hi, Alexander. Nice to see you. Thanks for the talk. I would like to know why the screening in the MACData database you don't find F or the P wave surface altermagnetism?
We didn't look for the odd parity characters because we only looked at the altermagnets which have even
This is
parity.
collinear. These are collinear systems that we're looking at.
Yeah, right, exactly. So we only looked at collinear systems. One can extend, of course, the analysis to the non-collinear systems, which then also have the odd wave character, but this would be analysis for the future.
Okay, okay. That means that the F wave is not for collinear system also.
Correct.
Okay,
Thank you.
great, great.
This add. It's quite
Okay,
fun.
okay.
Okay.
Thanks a lot.
Thank you.
Thank you, Raphael.
Well, I'm not sure if there's any further question. If you don't have any further questions from, you can always contact us, Alexander, or myself, or the team for any questions on this, what we believe is going to be a nice area. And thank you, Alex, for a wonderful talk as always. Yeah.
Thanks for having me.
And then to the rest of you, since I don't see any further questions, I'll thank all the 100 of you that have been watching directly, and then the rest that are watching afterwards. And please join us next week. I believe it's another talk, or the next talk. I'm not sure when it is, if it's next week or the week after. Okay. So thanks, everybody. And I'm going to now hang on. Let me try to stop here this streaming here. And the streaming now. So now you can say anything you like. It's not recorded anymore. But anyway, thanks everybody again. Then we'll see you guys